Hey guys, good to be here today. I'm here with Sebastian from HOPR, and hopefully we will get to talk a little bit about mixnets, what Sebastian's working on, and kind of the future of network level privacy, which is a very interesting topic. Maybe you want to give a little intro on yourself, Sebastian, and how you came to working at HOPR or running HOPR.
Yeah, thanks for having me, first of all, Keith. It's amazing to talk about privacy here, topic that's interesting to both of us, I guess. So, yeah, my background is actually in engineering. I have a PhD in microtechnology, and kind of after graduating, I co-founded a fintech here in Switzerland. And kind of there is where I've seen how innovation is kind of hindered, blocked, and slowed down by just stupid old world processes, which is really painful to see firsthand. And yeah, so around that time, that was now like 5 years ago, I became really interested in crypto and to see what it could do to us and what would allow us to do. So I'm really a passionate fan of permissionless innovation on public networks. Yeah, and then I've been after I got out of this fintech, which was really pivoting more to legacy finance technology, I knew, okay, this is not what I left the academic world for. I want to go all into public permissionless crypto. And so I've been educating people in the space. So we were in 2016 kind of the first continental European company which was giving workshops and showing people what Ethereum is and why it's amazing. We implemented a lot of projects throughout 2017 when tokens were a hype, and that's where we have seen that there is a fundamental problem, and that is that data are secure, but it's not private, right? In the Web3, as you send data around, it is secure, so largely it cannot steal your money, but you're not exactly very private. So I can, and maybe we can get to that later, I can extract all sorts of metadata about the connection that you're making, with whom you're communicating, and so on. And yeah, so that's what we set out to solve, and that's what the HOPR network seeks to do.
Okay. Can you tell me about like the network itself? Like, how does it work? There's like staked nodes that are routing packets. Do you have to pay to route data, for example? And like, what's the kind of topology that you're using?
Yeah, so starting from the problem of, I want to send data to Key, and I don't want to expose myself, right? So you don't need to know my IP address for us to communicate in the digital era. So, and also my ISP, my internet service provider, does not necessarily need to go that the two of us are communicating right now, right? So we think that's fundamentally private metadata information. So how do we go about solving that? So instead of me communicating directly with you, as is the case in many peer-to-peer networks and also other Web 2.0 applications, we're sending data via multiple intermediate relay hops. And these hops are relaying data. That's what the name HOPR should kind of reflect. And by doing so, by basically hopping data packets via multiple intermediate nodes, you're kind of obfuscating where it came from and where it goes to. So both the sender and the recipient do not know one another, and nobody can observe any sort of metadata information. So what we do there, so some here might be familiar with what I just described and say, hey, that sounds just like Tor. And that's right. So what I just described, this multi-hop routing of information, is actually exactly what Tor does. And HOPR actually goes one step further, because what many people don't know is Tor is not very private. It is relatively easily possible to de-anonymize Tor, so to figure out which sender was communicating with which recipient on the other end. And yeah, so to improve that situation, HOPR is employing what we call packet mixing. So every hop along this route is not just passing information on straight away, but they are transforming it, so data that comes in and goes out looks different, and they're mixing it up in other packets. So let's say Alice is getting this packet from Sebastian, and she is receiving a bunch of other packets also. she transforms them and mixes them up. So the order is different between incoming and outgoing packets. And therefore, even her internet service provider cannot link incoming and outgoing packets. And that's really powerful. And that's how mixnets are more private than your garden variety VPN or even Tor.
So can you explain, like you said onion routing, or well, you said Tor specifically, but onion routing suffers this problem in general. There's like several attacks that can be placed against it. Can you explain like what some of those attacks to de-anonymize end users are, like, and how they would work?
Yeah, so there's really a range of attacks that people, de-anonymization attacks against Tor that have become known over the past couple of years. And Tor is, it's providing okay privacy, but it's not really providing strong privacy against what we call this global passive adversary. So somebody who can listen to all the traffic in the entire network, which is not just, your favorite three-letter agency, but also powerful tech companies, right? Like internet service providers and international internet service providers that might be colluding with cloud operators. So one way that you can kind of link, and again, the attack here is not to kind of break data or kind of man-in-the-middle attack, but the attack is really a de-anonymization attack. So I can link the sender to the receiver. And here's one example how you can do that. So if I'm a user of Tor, maybe I'm using the Tor browser, that's what most people are probably familiar with, right? My computer from my router at home is sending a data packet to this first Tor node. It's also called the guard node. And it's sending a bunch of packets. Let's say the first packet is 123 bytes, and the second packet is 555 bytes, right? So it's kind of like uniquely sized packets. And they're traversing through this Tor network that I assume is private. But then on the other end, when it leaves the network in the so-called exit nodes, I see again a packet that is 123 byte, followed by a packet which is 555 byte. So this sort of, that's a very simplistic example, but this sort of packet fingerprinting is possible in Tor, because packets do not really look indistinguishable from one another as they enter and exit the network. And also, so this means this sort of attacks are possible if the first and the last node are colluding. So if you have really a lot of nodes in a Tor network, you can break that, right? So if you have enough nodes so that you accidentally control the first and the last node in the network, and given that there's not so many nodes in the network, there's only about, I think, under 1,400 exit nodes. That's not so hard, even for well-equipped individual players. But it's not just an attack vector that these, that's something I find important. It's not just an attack vector that players in the Tor network can launch. If your internet service provider and let's say the hoster on the other side are colluding, they can also de-anonymize it, right? So there's really a whole range of parties that can attack the Tor network. And again, that is because the trust assumption is the first and the last node need to be trusted and not collude.
And how does that like threat model compare with mixnets? For example, if the first and the last node in a mixnet are compromised, does that also have an effect on the user's privacy?
Yeah, that's a great question. So a mixnet has fundamentally way stronger privacy guarantees. So in a mixnet, actually, if let's assume the first and the last node are compromised, right? So in that setting, they still have no clue that the packet that the first one just received, which was forwarded, mixed up by the second node, is then received by the third node. Because I didn't mention this, but like typically mixnets have also 3 hops. You could have multiple, but HOPR has up to 3 hops in between. So there's one intermediate honest node remaining, and that one is mixing up traffic. And if we observe everything we can, again, think about this global passive adversary view. They see a bunch of packets going into the middle mix node, and a bunch of packets going out of this mix node in the middle. And maybe a few of them are hitting this last node, this exit node. In that setting, you still have strong privacy guarantees because you cannot do a better job than guessing, which packet went where. And if there's sufficient traffic in a network, then that's good enough. So that does still provide strong privacy guarantees.
Yeah, that kind of comes to one of my other questions, like something that you read a lot about in the literature about mixed nets is cover traffic. So can you explain what cover traffic is?
Yeah, absolutely. So before we get to this cover traffic, let's establish one really annoying kind of trade-off that all these sort of networks have. And that is the so-called anonymity trilemma. You have a trade-off between strong anonymity, low latency, and low bandwidth overhead, right? So you cannot optimize for all three of them. So you can have strong privacy if you're willing to incur super long latencies. So imagine on every single node, you're waiting, let's say, 10 minutes, right? Which is kind of crazy if we're thinking about applications such as, chat, for example. That would be crazy, right? You have to wait 30 minutes. But for some other applications, maybe email or something like this, maybe that's good enough. So if you're willing to give up low latencies, you can get relatively strong privacy guarantees. And the third one is bandwidth overhead. If we have really a lot of packets going through this network and mixing, in our case, this Alice node here, right, that is after Sebastian, in that setting, there's really a lot of packets per second going through Alice. You don't have to wait so long, right? So there's this combination between bandwidth overhead and latency that you're willing to incur. So the more traffic you is, the shorter you have to wait to receive the same level of anonymity. And so what can we do to improve that situation, especially in an early stage network, which doesn't have so much organic traffic? So what you can do is you can launch kind of bogus traffic, right? So this bogus traffic is indistinguishable from real organic traffic that users are sending. And what you're doing thereby is increase this bandwidth, right? And by increasing the bandwidth, as we've seen this anonymity trilemma, we can wait a shorter time so that we receive acceptable privacy guarantees. And there's different ways of how people are dispersing this cover traffic in order to increase the anonymity of the overall network. And that's called cover traffic. And so in HOPR, we're also working on cover traffic that increases the privacy that the network can offer.
The cover traffic itself, what does it actually do once it gets to, say, the endpoint or the destination that it's intended to go to? Is it just dropped silently, or does it come back to the user? Because I saw some designs where the message goes through the system and then travels back to the user.
Yeah, so there's different implementations how you can do that, right? So you could use cover traffic that you loop back to the original sender, and you could use that for measuring purposes to find out, how good is the network and find out some properties, which is actually kind of useful. If you know that a route actually worked and you have a certain level of acceptable package loss, you could also just drop the packet at the recipient side and do nothing with it. So there's different implementations what people can do.
When you're talking about publicly deployed networks, my mind goes to some of the projects like the XX network and NIM. How do you think HOPR compares to those networks that are maybe going through a testnet stage or deployed right now?
Yeah.
Where do you see NIM comparing to those?
Yeah, so first of all, none of these networks are production ready. None of these networks actually offer strong privacy today, right? So that's important to highlight. None of these networks are production ready. So if you're looking to build truly private applications, none of these mixnets is ready. They're all kind of in the early testing stage where people develop some first applications on it. That includes HOPR. They can, earn some bounties for building some stuff, but none of that is really actually production ready in private. And so what differentiates HOPR is that we want to incentivize the most fundamental operation of the network, which is packet forwarding. So in these other approaches, there's different ways on how they want to incentivize the mixed nodes. And some of that is undisclosed, so NIM hasn't really released a whole lot how they're actually going to do that. At HOPR, we're quite transparent about how we're going to do that. We will have a packet-by-packet incentive scheme that does not break the privacy guarantees, and that's kind of important, right? So if you bring in a way that you would pay every single mixed node, and you would pay them always straight away, even in something like Lightning on Bitcoin or something, you could do that. But in this naive implementation, you would see, okay, now Alice got paid, now Bob got paid, now Charlie got paid, and you would basically leak the routing information on the payment layer, which kind of sucks, right? So HOPR differentiates from these other networks by incentivizing the most fundamental atomic operation of the network, which is packet relay. So you only get paid if you can prove that you have forwarded a packet. And to me, that is somewhat similar how many crypto networks work. Think about Bitcoin. Like a Bitcoin miner only gets paid when they can prove that they were just creating a valid block, right? So that's the most fundamental operation in Bitcoin, is creating blocks. And similarly in HOPR, if you can prove that Alice has forwarded her packet to Bob, Bob will come back to her with an acknowledgement that includes the proof that the correct packet, without having been tampered with, has been received by Bob, and therefore Alice gets some information from which she can derive a payment. So without going too deep, that was what we call proof of relay. So you can really provide evidence that you have done your job, and that's how we incentivize things without relying on gameable game theory on top of it, without relying on some centralized watchdogs that are kind of saying, okay, you've been doing a good job. And that is what is unique about HOPR.
Yeah, okay, that makes sense. Where do you were talking a bit about why these mixed nets are still not in production, and you mentioned a little bit you think that maybe some of the earlier reasons were just because internet speeds weren't fast enough. Is what's stopping them from, because obviously internet's gotten faster now, what's stopping them from being deployed now? Do you still think it's an internet speed thing, or is it just the technical development hasn't gotten far enough, or?
Yeah, so I think the other part is really incentives. How do you pay mixnet operators, right? We don't expect this stuff to magically work free of charge. So first of all, I think that's an illusion. If we want to bring it really to a global internet scale, it's not enough that you have the Tor network, 1,400 exit nodes, and expect that these guys are just supporting the entire world free of charge. That's just not going to fly. So I think really it has been how do you pay mixed node operators to really scale this? I sometimes say, imagine AWS, right? So Amazon Web Services. Would Jeff Bezos have launched hundreds of thousands of computers around the planet if people had the expectations that these computers are to be used for free? Probably not, right? Probably we would not have global cloud computing if everybody expected this stuff to operate for free. And unfortunately for mixnets, if you think about it, you do something that's privacy sensitive. How do you pay these guys? You could pay operators with PayPal, right? But as we've seen historically, everything that's even borderline questionable gets shut down by PayPal and credit card operators and so on. So there really was no way to properly pay these mixed node operators. So only since we've had kind of these public blockchains, which allow for cryptographic primitives that allow us to build, for example, payment channels, in our case, or scalable layer 2 technologies on top of it, like others. And in our case, this proof of relay mechanism, only since we have that is it actually possible to pay the mixed node operators in a privacy preserving fashion that is censorship resistant, because that's super important. People think about, hey, what's the implication of blockchain, right? I don't think it's NFT trading, honestly. I don't think it's, for people to make, more money faster. I think the application of these public blockchains is where you really need them, where there is absolutely no other way to operate without them. And I think mixed nodes are a great example of that. And to come back to your question, I think that the reason why we don't see them in operation yet is because this is super new technology, right? So only 4 years ago, we have not had advanced enough public blockchains that would allow for these systems to be built, right? So that's actually very, very recent, and there's a bunch of like extremely smart people out there which are on it right now. And you mentioned XX Network with David Chaum, who's actually kind of the godfather and inventor of mixnets and anonymous communication. So it's amazing to see that there's not just young people working on it, but also, you know, the godfathers of privacy systems now get to it and take crypto serious, look into these systems and see how we can build resilient and sustainable systems that offer privacy on a global scale.
Yeah, fair enough. When you're talking about routing on mixed networks, is it like onion routing where it's source routing, where I have, say, a list of the different mixed nodes in the network and I decide which hops I'm going to go through? Or is there a system where, you know, I send to a first node and it sends to another node and another node? How does it kind of...
Yeah, so you could, in principle, you could imagine different implementations of that. In case of HOPR, it's source routed, exactly as you said, right? So the source, the sender, is deciding which path the packet takes. And we think this is important because privacy is something that is subjective. Trust is something that is subjective. So I might trust Alice, Bob, and Charlie, whereas Key has maybe totally legitimate reasons to say, you know, Alice, Bob, and Charlie are terrible. I want to go via, you know, Eve and their friends. So yeah, so that's why we think that source routing is something that is important, and that is how we have implemented that one. So in HOPR, basically, you have this topology which everybody can see. So it's a topology of payment channels. That's what we use on the incentive layer between adjacent nodes. And once you read that payment channel topology, you can select a path between these nodes in order to send your packet.
On the model of like network topology, I'm assuming like the way that most mixed nets work, or the way that I've looked at most mixed nets and how they work, is that there's a dedicated set of nodes which are kind of the mixers in the system. And these are the incentivized set that are running 24/7. Has there been any thought or design put into like a more peer-to-peer architecture where the individuals that are sending messages to each other are acting as mixed nodes in the system instead of having a dedicated set of nodes?
Yeah, it's interestingly asking. So this exact design is actually what we currently have at HOPR. So at HOPR, you have really this peer-to-peer design where anybody can run a mixed node at any time, come and show up and, you know, be a mixed node. There's some issues with that, and that is, for example, what kind of sucks for a mixed node is if you have intermittent connection, right? Let's say the worst case example that I could come up with is the subway, the underground in, like, let's say London or New York, right? So every 3 minutes you're online for like 45 seconds, then you're offline again, then you're online again. That really sucks for mixed node performance. And the other one is that you do want, ideally, if you think what is the strongest possible privacy guarantees that you can have, is you want constant kind of maxed out bandwidth through these nodes. Why? Because if you have maxed out bandwidth, then you don't see any traffic patterns, right? It's hypothetical, of course, because that's very hard to engineer and not take down the system also, right? And that is something which, for example, on your mobile phone, probably you don't want, right? Not only do you maybe have a data plan that doesn't allow for that, also like your mobile phone battery would drain really quickly. So there are some issues with this. And the other one is that you have this issue of, for example, cover traffic that you have to distribute. And if you distribute it over an unbounded size of peers in a network, you have this problem of so-called thin traffic. So you have very little packets per second, minute, or whatever that go through each individual node. And that is a problem because it doesn't provide strong privacy guarantees for anyone. So yeah, how we're solving that at Hopper is to still allow anyone to play around with this, but only if you have a certain amount of stake in a network, kind of to signal that you're willing to participate, will you receive roughly proportionally more of that cover traffic to solve this thin cover traffic issue. But yeah, so it is possible. We will see once we move to a more production use of Hopper as opposed to this early application use that we have right now, how that is going to evolve and like how tightly we will restrict the set of actively rewarded mixed nodes.
That's interesting because I know like Tor, for example, is like bandwidth weighted. Like, so if you're a really high powered relay in Tor and you have a lot of bandwidth, then you will be given more paths, you know, to route people's data through. But it sounds like what you're explaining is like stake weighted routing, like where you have a higher chance of routing through people with more stake.
Yeah, exactly. And that is basically going in a similar direction as what you just described from Tor before, right? So if I'm a home staker and if I'm a home relayer, then maybe I don't stake so much and I don't get to relay that much traffic, and therefore I don't get to earn that much. But if I'm kind of invested in a heavy duty internet connection, like some fiber connection, and have like powerful machines that are running my mixed nodes, then you know I get rewarded more for doing so.
I know like mixnets are still a pretty heavy area of research, and this goes the same with onion routing networks as well. Do you like, is there anything that's recently come out that you've been really interested like to read and apply in Hopper, or is it more like a space where you think most of like it's a well understood space and now it's just about implementation?
I think there's really still quite something left to be done out there, even in understanding how these systems apply to other crypto infrastructure. I think that's something that I'm tremendously interested in. Just to give two examples, so we're currently working on a research project on seeing, you know, what are privacy limitations of the Ethereum beacon chain. So the proof of stake Ethereum network has a bunch of privacy implications that will benefit from using mixnets. And there was actually another paper just recently coming out on checking out the privacy of the Bitcoin Lightning Network and the usage of what is called Dandelion or Dandelion++, which is kind of a mix of kind of onion routing. So you have multiple hops, that's kind of like the stem of the Dandelion. And then you have something that just blasts in all directions. So that's kind of supposed to be like this budding flower of the Dandelion. And interestingly, what this paper has seen is that, you know, this kind of weird design of this Dandelion in case of Lightning doesn't really offer the privacy guarantees that people actually kind of inherently expected it does offer. So it's really the interplay between the private communication networks and the application that you use it for that I find really interesting. This paper on Lightning and Dandelion was really surprising, because like many times Bitcoiners are like hardcore privacy people also, right? Which is great. But yeah, unfortunately that was not enough. We need more than Dandelion if we want to keep things actually private.
Yeah, interesting. What do you think is next for like Hopper? You have this, I was on your website before and it looks like you have some test applications up, but it looked like there were about 40 nodes available, or there were 40 slots rather.
So that's our playground. And the idea for us here is that as we're working towards more and more stable releases of our network, we already want to give developers and users kind of an experience like, how does it feel like to use such a network? Because what we're going to do with Hopper is that Hopper will be deeply integrated in the applications that use it to, again, optimize performance. And so if you want to check that out, go to playground.hoppernet.org, and they can like play around with some of the quirky very first applications that are out there. So we want to build out this user experience, which, if you think about it in other terms, constitutes kind of like the demand side for private bandwidth on a network. And in parallel, we want to make the protocol itself more useful. So right now, HOPR has this kind of single packet-based API, so you can send packets right now, individual packets through the network. Ultimately, what we want to get to is that you as a developer don't need to bother about sending individual packets, but you have, you can open a socket connection, for example. So you can just say, I want to send a bunch of data to key. I don't really care how it gets there. You take care of all of that. So that's what I would call making HOPR more application developer friendly. And that's what we're working towards over the next 12 months, I guess, to make it more useful and more stable. And yeah, it's kind of both sides.
And do you have like libraries or packages that I can pull into like my current project or like a project that I would be working on as a developer to like use the network?
So what we currently have is just like a REST and WebSocket API that you could use. We don't yet have like an SDK, but it's certainly something that we will provide in the near future. So currently, what you can do is, if you want to use the HOPR network, you can run a HOPR node. And if you want like your dedicated access point, we're also selling these customized dApp nodes. So if you want to buy a dApp node on which you can not just run HOPR, but you could run an Ethereum node or whatever. So I would recommend that. And like through that, you have your kind of trusted access point to the HOPR network. And from there, you can consume the API already today and build it into your application. So that's going to be a bit more cumbersome. If that's too cumbersome for you, then I would recommend you wait for our SDK, like something like a HOPR.js or something, right, which you can pull into your application and just say, send data to Keen. I don't want to care about anything else here. Yeah, that will be possible, absolutely. And maybe lastly, a thought just that I think about more, and I sometimes find people surprised with that, decentralization is great. But decentralization doesn't solve all issues. Decentralization might actually make us end up in a world that is worse in many regards than the Web 2.0 that we're used to, with regards to data harvesting, with regards to individual user privacy. So the Web 3 really is anarchy, right? There's no rules in the Web 3. It's like this wild world where people and companies and projects interact with one another, can build on top of one another, which allows for great innovation and really fast-paced innovation. But at the same time, you cannot kind of order this chaos of Web3 with regulation because it's resilient technologies. So the only way to make the Web3 a safe space for all of us, if we have strong privacy across the stack, right? So without strong privacy, there is no safe Web3 for anyone here. So if we want to make this space go absolutely anywhere, we really need to think hard about privacy on all sorts of layers. And again, HOPR is just like on the transport layer. There's on-chain privacy, and there's a ton of other issues that are unresolved as of now that really must be resolved by the time we onboard all sorts of normal internet users to a safe Web3 for everyone. And that's what we need to do.
Yeah, well, I strongly agree with you on that one. It's not hard to convince me of that. Yeah, did you want to like shout out anything? Like, how can people find out more about HOPR?
Yes. So hoprnet.org is our website where you can find out more what we generally do. If you want to play around with it, I mentioned it already, check out playground.hoprnet.org. It literally takes 5 seconds and you have like your own set of HOPR nodes. You can play around with some HOPR apps. If you want to build your own HOPR app, similar to the ones that you see there on Playground, check out bounties.hoprnet.org. So on bounties.hoprnet.org, we always have an increasing set of developer bounties to build something yourself. So if that doesn't show what you want to see, come talk to us. We're open to like freestyle bounties for people to work on. And yeah, follow us on Twitter and all crypto events where you happen to be. We like to talk to people that are interested in privacy. Come talk to us. Don't be afraid. We want to make this, we want to change data privacy for good. And we need all of you to work together with. Like privacy loves company, as people say.
Yeah, I'll just say it's very easy to spot you at conferences because you're wearing all yellow and have HOPR stickers all over your clothes.
Exactly. So I'm currently in my conference gear, so that's how I look like. Yeah.
All right. Thanks for talking to us today, Sebastian.
Thanks for having me, Key, and thanks for putting a spotlight on privacy, and thanks for pushing the topic yourself forward in such a beautiful way. And yeah, having apps that actually hundreds of thousands of people use out there is absolutely impressive. Kudos for that.